here and to have the opportunity to give a talk about some interesting results I have obtained during the last part of my PhD in Padova. And they are about the sound propagation in two-dimensional atomic gases, and most of the results I'm going to present you are contained in this paper published last year on Physical Review A. So let's begin by okay, sorry. Let's begin by giving you an outline of the presentation. First of all, I'm going to talk a little bit about two-dimensional superfluid and the reason why they are so interesting. And the fact, in my opinion, is obviously the occurring of the Berezinski-Kosterlitz-Thouless transition. Then we are going to discuss how can we observe this transition. And in particular, I'm going to present the recent experiment by the group of Jean Dalibard at the École Normale in Paris. And then we discuss their unexpected result and a simple way to explain their observation based on a kinetic approach, and in particular on the two-dimensional Landau-VLASOV experiments. We describe the propagation of sound in a collisionless 2D Bose gases, and we compare our analytical results with the experimental observation of Jean Dalibard. Then at the end, I want to give a brief comment about the Zaremba-Nikuni-Griffin, which provides, in my opinion, a very transparent way to describe Bose-Einstein condensate at finite temperature. And then we summarize and we talk a little bit about the results and the future's perspective. So, from the basic courses of statistical mechanics, we all know that for an ideal gas of identical bosons, we have macroscopic occupancy numbers of a single particle state only below a certain temperature. We can solve this simple equation for the critical temperature in a generic dimension, and we see that we have a finite critical temperature for 3 dimensions. The critical temperature becomes 0 in 2 dimensional, and we have no solution for a 1-dimensional system. This simple result, due to Einstein, can be extended by means of the Mermin-Wagner-Hohenberg theorem to interacting system. And more precisely, what the Mermin-Wagner-Hohenberg theorem tells us is that we cannot have true long-range order and then Bose-Einstein condensation for homogeneous system at finite temperature at dimension lower or equal to 2. But everybody here knows that two-dimensional system can exhibit all the hallmarks of the superfluid behavior. And the reason is that another phase transition occurs, and it is the Berezinski, the BKT1. This transition is due, I'm not going deep into the detail, but it is due to the topological detail of the order parameter, in particular to the bound support of the phase variable. And we can observe this transition is an infinite order one, meaning that we do not have discontinuities in the thermodynamic function. But the smoking gun of the transition is that the superfluid density jumps to 0 at the critical temperature. It is possible to confirm experimentally the occurring of the transition by performing experiments on the helium-4. And this is the case of this paper at the end of the 70s by Bishop and Reppi. They simply perform the Andronikashvili experiment with the torsion pendulum in a 2-dimension, in a thin film of helium-4. And we see that below a critical temperature, the superfluid component decouples, and we have a decreasing of the oscillator period. We can also observe the BKT physics in thin superconductors, and also the BKT crossover and vortex proliferation in trapped BC. In particular, I point out this experiment back in 2006 by Zoran Azibabic and Jean Dalibard. Recently, we have also some measurement about the BKT temperature for 2-component fermionic atoms, and we can try to capture in a simple way the behavior of the critical temperature by using the Nelson criterion, which describes the universal jump of the superfluid fraction. And we only have to be careful about the fact that the depletion of the superfluid is driven by the single particle fermionic excitation and also by the bosonic fluctuation, the bosonic excitation of the pairing field. So we have, we have two different components of the normal fraction, different contribution of the normal component. So at the end, we have the most striking differences between 3D and 2D superfluid is the fact that the superfluid fraction jumps to 0 at the BKT temperature. Dealing with cold atoms, which other quantity can be measured to reveal this universal jump and characterize the transition? The idea of Jean Dalibard at the École Normale is to measure the velocity of sound. Indeed, by making use of the LANDAU-VLASOV model, we know that we can have two different sound. We can have two different propagation modes for the sound. In particular, in 3 dimensions, we have the first sound, which is an in-phase oscillation between the normal component and the superfluid one, and the second sound is, on the contrary, an out-of-phase oscillation between the two components. In 2 dimensions, if I remember correctly, the situation is reversed, and most importantly, the second sound velocity, which is the green line, is below the first sound velocity. The interesting point is that the second sound velocity is proportional to the square root of the superfluid fraction, so it should jump to 0 at the critical temperature, at the BKT temperature. So this was the whole.
Was inverse, because I thought the first sound is always faster than the second sound.
It's not the case. In TrueDym, it is true if you're working with helium, but there are some differences in the analysis if you're working with cold atoms, which are much more diluted than the helium-4. If you want a reference, there is a very clear paper by Sandro Stingari and Tomoki Ozawa, where they explain this difference between helium-4 and cold atoms, BC, and also fermionic systems.
So that is because of the weak interaction, not because of the dimension.
Yeah, because of the weak interaction, yeah. This is not a dimension-related effect. You're right. The dimension-related effect is the jump in the superfluid in the second sound velocity, because the second sound, I want to stress again, is proportional to the square root of the superfluid density. So this was the hope of Jean Dalibard, but unfortunately, when they tried to measure the second sound velocity in their rubidium setup, they observe a strong discrepancy between the true fluid prediction and their experimental points.
Can I ask a question? How do you distinguish experimentally between the two sounds?
I'd say that the criterion is which is faster, which is faster.
You have to measure something. For the first sound, it's clear. You look at the waves.
In 2 dimensions, it's more clear because the second sound corresponds to a density perturbation.
No, but how do you see it?
You can prepare a state in a box potential. You can prepare your system in a box potential, and then you can excite a sinusoidal perturbation, and we see how this perturbation evolves back and forth your system. You see only one way in the experiment of Jean Dalibard.
So which is that? Is the first or the second?
Neither of two. Neither the first sound and neither the second sound. Because the point is that in the experimental condition of Jean Dalibard, the true fluid model is not reliable. And the thing is that in order to rely upon an hydrodynamic theory, you have to assume local equilibrium. So you have to, basically you have to say that collisions are strong enough to thermalize, to provide that the system goes to the equilibrium, and it is not the case in the Jean Dalibard experiment.
So your point is that they didn't really measure that?
They don't measure the second sound.
But that you want to measure. How do you measure? You see the two sounds. See, this is my question. So let's assume you do it in helium. So how you're going to distinguish between them? You see, because sound, you see, I talk to you, I know how to distinguish.
I think that you can
distinguish the second one.
There's supposed to be a temperature oscillation.
Yeah, you can see which perturbation is in phase between the normal and
so you measure the temperature
well, basically,
variation and the density
for helium, second sound is an entropy wave because
but you have to measure entropy, right? So how do you measure this is my question.
you can see a temperature wave, I think, in 3D. In 2D, in order to observe the second sound, you can observe second sound because second sound is a density perturbation. So you simply have to pin the two-dimensional system and to observe the evolution of, for example, a sinusoidal perturbation.
I'm sorry?
Also, first sound is the density perturbation.
But,
Yes.
but the difference is that you have an in-phase or an out-of-phase oscillation between the components.
Yeah, but how do you distinguish the two components then? Okay, so how do you distinguish normal and super?
Normally, you drive the second sound by temperature.
But that's 3D.
Right.
I mean, as he says, this is not.
And in 2D, the situation is reversed. Yeah,
So what is the frequency? You see, you have to drive this, you have to have, I don't know, a speaker, you see, where the speaker encodes a temperature, you see, which you have to drive relatively fast. How do you do that?
Oh, so in the 3D experiments, it's, you just have a heater and you have a current going through it.
But how fast do you do that?
I've never done these experiments and I'm not going to know.
Yes, because I assume you see the frequency, usually it's hertz, you see hundreds and kilohertz and so on, you see, although it varies so fast.
So if you say one is in phase and one is out of phase, do you mean in and out of phase with your perturber, or
which is?
with your perturber, with your perturbing force, or what does it relate to this in and out of phase?
Basically, in phase, out of phase, you have don't
I
see.
think this is in theory, you see, okay, the delta phase.
Yes.
The question, how do you see it in experiment?
Yes, I just try to grasp it in the first place.
I feel, I don't know how to answer exactly to your question. I think that the hope of Jean Dalibard was to observe a sound wave which jumps to zero, whose velocity jumps to zero at the transition. So because from the theory, you know that a sound velocity that jumps to zero at the transition corresponds to the second sound.
Well, theory does calculation at the same time you have an observable. So what's the observable? They have to detect something, you see, but if you say they're out of phase, I have to detect at the same time the superfluid and normal component. So I have a detector for those. How do I do this?
From what I know about the experiment, they simply observe the velocity of the density perturbation. This is what they do.
But they see the density of the normal component or the superfluid component?
Total.
But then how do you see it? Because in the out of phase,
That's
they
the
compensate.
experimental result, and now you have to come up with a theory that explains it.
Also, the main point is the main point of the talk is that they don't see neither the first sound neither the second sound.
So let's come back to the definitions of sound and how we go back to it.
We're talking about theory, they're talking about experiment, and I want to confirm the truth. I want to understand how you do this.
Yeah, but in fact, they were using the wrong theory. They were using the wrong theory. Indeed, we are not deeply in the collisional regime where you can rely upon the sorry?
Yeah, as you said, the important point is that in the diamond gas, the collision rate is small.
Yeah.
So that thing, the two-fluid model is actually not better. So.
Yeah, the point is that you cannot take the two-fluid model for granted.
Yes,
you have to test that you are entitled to use. A
long time ago, Jason Ho has this prediction about first and second sound, and then the Russian guys, Prokofiev and Svishnov, already criticized that paper, and so I think the story comes back again. Yeah, the collision rate is just too small for the interacting gas.
And so what we try to do is to explain this discrepancy between the theory, the two fluid model, and the experimental results, is to use the most simple, the simplest kinetic approach, which is a collisionless equation, nothing else than the Landau-VLASOV equation, which is common in plasma theory. And there is a slight modification to what you know from plasma theory, and it is the mean-field interaction potential, which is modeled around an Hartree-Fock mean-field term. And this function is the single particle distribution function. And another reminder is that short-range coupling constant is not simply proportional to the S-wave scattering length, but instead it depends on the ratio between the S-wave scattering length of the original 3D problem and the characteristic confining length of the harmonic confinement on the frozen axis.
Question concerning that equation as well. There's nothing else by the semi-classical approximation of the Schrödinger equation.
Of the?
Schrödinger equation.
Okay.
So I can do the semi-classical approximation, derive that because I don't have the collision integral. So I can derive that directly right for any Schrödinger equation. Why solve the semi-classical one and not solve directly the quantum equation?
Because strictly speaking, for example, you do not have condensation in two-dimensional. So, for example, in the mean field of Z and G equation, I have an equation for the condensate, an equation for the thermal cloud.
But here you still have a single component. You don't have two of them.
Still have?
You have a single component here.
Yeah, I have a single component.
But a single component means a single wave function. So I don't understand why you do that. You see, what's the reason to do that?
What do you mean that a single component?
Well, I don't have normal and superfluid component. I have one single component. And if I have a single component, I can describe it in wave function. And if I construct the density matrix, and after that I do the Wiener transform, the single transformation, I can exactly.
Yeah, you were saying that one.
But but that's an approximation. You see when you do that, because you forget, for example, the quantum pressure term, which you don't have here. But you see, if you go to the Schrödinger equation, you'll have all the terms there. You don't have h bar, but in the initial equation, you'll have an h bar there, so which will be in the quantum pressure term. So why do you resort to this and don't do the Schrödinger equation?
Maybe because first thing is, I think it's easier to derive.
So it's easier because this will be, in your case, will be a 4-dimensional equation.
Yeah.
Schrödinger equation will be 2-dimensional, so this is not easier.
I have to think about this, but I'm simply thinking about, you have a collisionless system and you try to think about the most simple way to model it from a kinetic point of view. And so you have to rely on.
Kinetic means collisions and you don't have.
No, kinetic don't mean collisions. It's not the same thing. I mean, the Boltzmann equation, you can try to put a relaxation time approximation and you can try to.
But you still have collisions. That's kinetics. Kinetics means collision.
Yeah, but indeed,
entropy production.
The collisions are not strong enough to provide local equilibrium. So
we don't have entropy production. In kinetic approaches, you have always entropy production. Here, there is no entropy production.
But this is a hydrodynamic equation without a collision term, isn't it?
You speak too softly.
So this is a hydrodynamic. Sorry, yeah, it's a microphone. Okay, no, I was just saying this is a hydrodynamic equation without a collision term, isn't it? So it's correct. From that point of view, it's not correct.
No, you can write the Schrödinger equation. For the Schrödinger equation, you construct the density matrix. You take the Wiener transform, and then neglect terms. You see these h bar high order terms. You obtain exactly the equation. So that's an approximation of the Schrödinger equation, nothing else.
Yeah, okay.
Which you forgot, you see the quantum curve.
Yeah, I think you have done a lot of fermions. I mean, for fermions, you have exactly this equation for the Fermi gas if you ignore collisions and so forth.
Well,
this is the Landau equation. This is the Landau kinetic equation.
No, we can talk about fermions.
Bosons.
Yeah, you have to say that thing.
No, he's talking about bosons.
I know he's talking about bosons, but that is actually just the kinetic equation. That is the occupational number for R and P. It's exactly the form of the
No,
Landau-VLASOV
it
equation.
is, because if you
Landau liquid theory is exactly that equation.
All right, let's bring this back to this afternoon. We have some discussions. We'll come back.
Anyway, I would understand this.
So, what we do is to perform a linear analysis on this equation. Namely, we perform a small perturbation of an initial state, which is stationary and isotropic. And if we move from the real space to the Fourier one, to the reciprocal one by means of a Fourier transform, we can derive this implicit equation for relating the frequency to the wave vector. And this is very similar to what you see for Landau damping in collisionless plasma. So really nothing different from a formal point of view. The difference is that, just some technical detail, you see that the only way that if we take the frequency as a real quantity, we have a singularity on the integration path. And so the only way to attach, one way to attach meaning to this integral is to consider the frequency as a complex quantity. And this means that we are assuming that our perturbation is damped. And then, without loss of generality, we can assume that the perturbation is parallel to one principal axis. And then we see that all the dependence on omega and k is through their ratio, which has the dimension, obviously, of a velocity. And this is what we call the velocity of the collisionless sound, or zero sound mode. Now we have to give an ansatz for the initial state, and since we are dealing with two-dimensional bosons, we choose to use the Bose-Einstein distribution function, which we approximate to this formula. And this formula holds if we are below the Bose degeneracy temperature, which is reported here. And so we have another small trick, and here we have the dependency on the short-range coupling, on the Hartree-Fock interaction, and one way to remove it, formally remove it, is to define a shifted chemical potential. And so, through the normalization condition, we are able to derive the equation of state, which relates to the shifted chemical potential, the temperature, and the number in the density, which appears here in the expression of the Bose degeneracy temperature. Under the assumption of a weak damping, meaning that the imaginary part of the sound velocity should be smaller than the real one, we are able to derive two equations, one for the real part of the sound velocity, one for the imaginary one, and we see that these equations are not elegant, they are very cumbersome, but nevertheless they can be solved. And the interesting point is that there is a good agreement between our collisionless theory and the experimental point of Jean Dalibard. Here we see blue, the experimental points. The dashed line is the undamped theory, meaning that we have put the imaginary part of the sound velocity to 0. And now we have our collisionless theory. I have to remark the fact that this increasing behavior, in my opinion, is not physical, because here there is a breaking down of our weak damping assumption. Indeed, if we see the inside of this figure, we see that at the temperature 1.2 of the critical one, we see that the imaginary part of the sound velocity begins to explode, and so we cannot do the weak damping assumption.
Can you back up one slide? Just the experiment, the previous one. Yeah, that's right. So what is the expected BKT transition for their system?
Or what do you mean? Where is the point of the BKT transition?
Yeah,
sorry, I write this C, but you should write BKT. The temperature in this case is a unit of the BKT temperature. And you can derive the BKT temperature from the universal relation provided, for example, by the quantum Monte Carlo simulation by Prokofiev and Shvishnov.
I see. A little bit surprised because then your FRP, you go back one slide. For the FRP, you have this, go one further back. So the way that you assume over there is precisely actually assuming that your gas actually is not condensed. Right? Because that's just your equation is the same as the normal.
In 2D, you don't have condensation.
But then even at equilibrium, your equation do not describe a phase transition. Your approximation excluded that because you actually have to include these log time terms to get you the BKT transition. And now you are saying that kinetic equation, ignoring all this, actually gives you.
Yeah, you're right. We're not accounting for the BKT physics here.
Yeah.
But the point is that basically we are interested in see what sound mode the experiment is exciting. And you're right. A unitary analysis of this phenomenon, including the second sound, the superfluidity, and the BKT is still missing. So you have to, in my opinion, you should write down a kinetic equation plus an equation for the superfluid part.
I know that part I agree, but I'm just saying that your starting equation is basically has no difference from the normal thing. Your starting equation.
Yeah, but okay.
Right. I mean, there's this interaction. There's this log term that
you can interpret these things by thinking that this phenomena, this sound mode, is mediated only by the normal component.
That's the conclusion. Okay, fine.
Just one silly point. CR is defined as the point where the real part of the.
Sorry.
CR is defined as the point at which the real part is.
Yeah, you see, C is omega, the ratio between omega and K. So omega is a complex quantity. So you have a real part and an imaginary one, and so you can split C in a real part and an imaginary one. Okay, so it is now the right thing to do is to acknowledge a complementary analysis by the group of Sandro Stringari and Nick Bukakis in Trento and Newcastle. Basically, they obtain results that are very similar to ours by means of the random phase approximation plus the sum rules. And most importantly, they provide a numerical check by using the stochastic GPE equation. Yesterday, we talked a lot about the stochastic GPE equation. So you have a classical field, not only describing the superfluid of the ground state 1, but also a certain number of excited states below a cutoff. This projector ensures that you are projecting on the chosen states. And then you have the noise term, which models the interaction between the chosen states and the states as higher energy acting as a thermal reservoir. The noise that we show is a white one. And now we compare our result with the Stringari one. You see that the result of Sandro Stringari are better than ours because they don't have this physical tail. And the reason is that they don't perform the weak damping approximation. And then another consistency check is to compare our analytical, very simple, very naive. I may agree with you. The choice to use a collisionless equation may seem naive, but otherwise, if you are going to compare our prediction for the compressibility with very rigorous numerical simulation, you will see that we have a good agreement. Indeed, here we have the solid black line is our collisionless theory. The red point are the simulation results performed by Nick Bukakis, and we have also reported the QMC calculation by Prokofiev and Zvishtinov. Moving forward, now I want to briefly mention, we can discuss later about the validity, the reliability of the ZNG equation. But maybe my naive understanding is that in 3 dimensions you can model a finite temperature BC by considering the two-coupled equation. An equation for the condensate or the superfluid part, which is nothing else than a GPE equation with a source term accounting for the interaction, coupling the condensate to the thermal cloud. And then you have the Boltzmann-like equation where you have two different collisional processes. You have this collisional integral describing the interaction between two thermal atoms and one condensed particle. And then you have the collision processes occurring in the thermal cloud where you have an interaction between two thermal atoms. You're right, Professor, the single particle distribution function has to be intended as expectation value over some ensemble of the Wigner operator. And all these things are detailed in a very nice way in this paper by Zaremba, Mikuni, and Griffin, where they provide also the analytical expression for the collisional integral, which are, again, a little bit cumbersome, but you can do some things with it. For example, they are able, in 3 dimensions, to move from their framework to the two-fluid model of Landau and Kalatnikov. So, moving to the conclusion, what we have presented in this talk are some basic features of 2-dimensional superfluid, some way to directly observe the BKT transition, and a possible recipe to observe it in 2-dimensional bosonic system. By assuming a 2D configuration, we have modeled our system in a very simple way by means of the Landau-VLASOV equation, which we have solved, and we have derived a couple algebraic equations for the real and imaginary part of the sound velocity, and in particular, the real part is in very good agreement with the experimental result of the experiment of Jean Dalibard. And in the end, our analysis strongly suggests that the density perturbation that Jean Dalibard used in his experiment has excited the so-called bosonic zero sound mode, which is nothing else than the sound of a collisionless bosofluid. Perhaps the most important message from my talk is that you cannot take the Landau two-fluid model critically. You have to check if you're modeling a real system. You have to check that you're working in the hydrodynamic regime, so you have to be sure that you are deeply in the collisional regime. Concerning future perspective, we surely need a theory accounting for the second sound or something related to the superfluid density in 2D bosonic system. And also we should be able to describe in some way the crossover from the collisional to the collisionless regime, which is a thing that is missing from my theory. And I agree, from a rigorous point of view, may seem ingenious, but the principle, the aim was to try to give an explanation of the observation of Jean Dalibard. So in the end, I thank you for the attention. Sorry for eventual mispronunciation. And if you want, I can share you our paper. I can give you references. I think we can discuss later. Thank you very much.
Thank you. All right. I'm a little bit confused. So you used the Landau-VLASOV equation and you said somehow that excitations are in the normal fluid. Well, that's why kind of the propagator was, I think, that of free particle essentially in there.
Okay.
Now you're saying you're describing these modes as the normal sound modes across the BKT transition, but is there anywhere a sign of the transition and of this coherence in your equation such that you can actually see this? I don't see how this fits together somehow.
Yeah, the only way in which the BKT physics enter in our description is the way we scale the temperature. Basically, we scale the temperature in the units of the BKT temperature you're expecting for a system with that density and that coupling constant. So I agree. Basically, we are not talking about BKT transition in my analysis. The point is that, from my understanding, the observation Jean-Dalibard are only driven by the normal component from the thermal atoms. But again, I agree that the big point missing from my description, from my analysis, is how the superfluid and the normal component are interacting. There is an hybridization of the mode. There's still a lot of questions to answer. So I agree. This is an important point that should be discussed later on.
Can you show the result, the experimental plot they have? See what you said this is, because this is the experimental result. So they definitely measure something above the critical temperature.
Yeah.
Correct? So they don't have the superfluid component. That's I think the. So why is this unexpected? Because you have sound.
Because you were following the prediction of the theory and you were expecting to observe nothing about the transition.
If you measure the regular sound, that exists everywhere. So you see, and then you can do kinetic approach, you see it especially about the critical temperature. So what is here the surprise? See, you have sound about the critical temperature, normal sound. And usually take that from kinetic approach.
Not in the collisionless image. Well,
you see, the question, you see, what's the rate of the collision and so on. You see, that's another question. So you have to look at the frequency of the collision and the frequency of the sound, you see, compared to two. You see, so you look at low frequency or high frequency and so on, so you have to distinguish that. So if you look at the low frequency, then collisions will be there, very low frequency. So now the question is, what frequency they see, what frequency they measure. See, are they in the collisional regime or collisionless regime? I don't know, because for me it's not clear. But if they are above the critical temperature, they should see the normal sound. And if they continue going, you see below.
Yeah, but the normal sound, the prediction of the normal sound is higher. You should see higher velocity. I agree with you that you should see something.
I'm not clear what they measure. You see, for me, it's not clear what is measured, what they perform. What did they measure? You see, they should have a detector of something. What did they measure? Density? If density, that's the normal sound. Right?
That's the density.
Yeah, so that's the normal sound.
No, but they're just measuring the density correlation function, right?
I'm sorry?
They're just measuring the density correlation function. And that need not be sound. It's sound.
Why do you say density correlation? I didn't see that. Do you make it up or what?
I mean,
well, you see, I understand that they measure the sound wave. The sound wave, you don't measure density correlation. You measure sound wave. You look at the bump, you see how propagates. It's not velocity.
You put the particle potential will couple to the density, and then the response is the density.
Like the work of Sandro Strigari in the LANDAU effect.
So if they measure density, that's the normal sound.
No. They can't.
Only when it is. Only when you have lots of collisions, that would be your ordinary understanding of sound. Because that's actually what
I didn't say about the understanding. No, understanding is another question.
Yeah.
If you measure density, then you measure normal sound. If you measure temperature variation, that's the second sound. If they measure density, that's the normal sound.
Yeah.
What's the origin? It's collisionless or collisional? That's another question. But it's a normal sound.
So they measure density.
Yeah, so that's a normal sound.
So the experimentalists, the experimental paper, thought that they were measuring second sound because the frequency matched the expected second sound frequency better. And then they said, it's really surprising that it continues above TC if it's second sound. But I think it may be that the interpretation of second sound is just wrong.
That it could be, but
in the literature there is some problem in the terminology.
So what is the frequency that they measure, or what is the wavelength that they are?
I don't remember. I should check the experience.
You have CB there. What's CB?
Is the Bogoliubov sound.
That's the normal sound. It's not the
at zero temperature.
Yeah, it's the normal sound.
And in fact, our
So you see
going in the low temperature regime, we see that we are going to the Bogoliubov mode.
Yeah, but there's a normal sound. It's not a second sound. It's a normal sound.
It's
Well, a T equals 0.
Yeah.
Yes, by definition.
That's a normal sound. It's not a second sound. It's not the temperature variation. It's not an entropy.
I guess in two-dimensional, that is the second sound that goes to the Bogoliubov one. In two-dimensional, it is what happened.
How distinguish between the two then?
You can see at this point as a second sound is lower than from a theory point of view.
I had a question about the mean peak potential U that you had put in your equation. I think it was yeah. So
It's the regular definition.
It's just GN, right?
Yeah,
See,
it's just
when you integrate over P, you take the density from the density matrix. You look at it, and then multiply the coupling constant with 4.
So we can continue to discuss about what you call second and first sound, because
Any other questions for the talk? All right, thank you very much.